So here we go, chapter 4. This, I believe, I might even do the first 4 sections. We'll look at timing. The chapter 4 syllabus is here, and then also the formula sheet is given below. So these are the formulas that you are given, so it's nice you'll have some of them. It's definitely not all of the formulas that we'll learn. So just to make sure you understand the difference between a polynomial function is something like x squared. Exponential function would be 2 to the x. So here the exponent is a constant number. And actually I probably shouldn't call it a constant, but the easier way to say it is that the base is a variable. Here the exponent is the variable. That's the major difference between the two. Laws of exponents, I'm pretty sure you know most of these, so I'm not going to waste your time and go through all of them. Please make sure for this one you notice that you can do the denominator power first, which is the root, or the actual power on top, the m, can happen first. It doesn't matter which way. I put this in just so you could see what 3 to the x and then 1/3 x look like. They are reflected about the y-axis, and the real reason why, just to make sure you know, this is the same thing as 3 to the negative x power, so the reflection happens across the y-axis. Exponential functions look like this. Exponential functions will have an asymptote. The asymptote will be horizontal. You have exponential growth versus exponential decay. Your domain will be all real numbers, and your range will depends upon the horizontal asymptote and which way the function graphs, whether it increases or decreases towards the horizontal asymptote. All right, so use the graph to sketch the graph of each of the functions. We're just going through the transformations again. I just wanted to use this to talk about domain, range, and horizontal asymptotes. So let's look at A. G of x would equal 2 to the x plus 3. So a really quick sketch of the graph would be that the transformation is shifted up 3, so the asymptote is now at y equal to 3. 2 to the x, the y-intercept is shifted up 3, so now it is at 4, and the graph is increasing, looks like this. The domain would still be all real numbers. Your range, just like I said, depended on your asymptote, its y is greater than 3. You may also see that the notation in your book more so does this, y in the real numbers such that y is greater than 3. And then let's do C. Letter C, p of x is equal to negative 2x. This is going to have a reflection across the x-axis. And so the y-intercept, instead of being 1, will be negative 1. The asymptote is still y equal to 0, because that's the original. And in yellow, real lightly, I'll do the graph of 2 to the x. Therefore, the graph in red of negative 2 to the x goes this way. So domain, all real numbers. Range is where y is in the real numbers and y is less than 0. Because of the asymptote, we have to say less than. Exponential growth and decay. So exponential growth would be, and I'm going to use the notation your book uses. So a sub t is equal to a sub o times growth would be 1 plus r to the t. Your, I guess, b value, and I'm going to actually change this in a second. So 1 minus r to the t. That's usually for most real-life functions where we talk about percentage. Those are the formulas that we use. When we talk about basic exponential growth and decay, we look at something like this, which I believe is the function that your book has. And they look exactly the same. The only difference is that for the growth model, your b value is greater than 1, and your decay model, your B tends to be between 0 and 1. So your growth or decay factor is the B value. And in this case, this whole thing is the growth or decay factor. Okay? Let's look at this example. A sampling count of bacteria in a culture indicates that the number of bacteria is doubling every hour. Given that the estimated count at 1500 hours, so 3 p.m., was 12,000 bacteria, find the estimated count 3 hours earlier at noon and write an exponential growth function. So let's see. So in the problem, just because we're talking about 3 hours earlier, I'm going to say that time equal to noon, so 12. We're going to just start our problem there. T is going to be equal to 0 there. So at 1500 hours, your T is equal to 3. The sample count doubles every hour. So from there, we know some things. We know that the amount at 3 was 12,000. We know that the formula would be, let's see. Well, before we get to the formula, we actually also know that the rate, the growth factor, would be 2, because we're doubling. So A sub 3 is equal to A sub O times B to the T. So let's fill in whatever we can. We know that 12,000 is equal to, we don't know A sub O, but A sub O is what we're looking for, the amount at noon, times B to the T. This is after 3 hours, so your A sub O is equal to 12,000 divided by 8. So that would be the amount that we are starting with. 15,000, I believe, is what that ends up being. Or sorry, 1,500 bacteria. And then the function would be A of T is equal to 1,500 times 2 to the T. All right, moving on. Half-life formula is given here. So however long it takes for a half-life, you essentially put that in the formula itself. So when we look at the H is the time it takes to half. All right, so the half-life is approximately 5,730 years, so that would be your H. How much of a 10-gram sample, so that's our A sub O, remains after 15,000 years? So we're looking for A sub, the time would be 15,000 years. Our initial amount was 10 grams. We're half-lifing this, and the time is 15,000 divided by the amount of time it takes. And when you put this in the calculator, please remember an extra set of parentheses there. And so the value is approximately 1.63 grams, which is what your book has. I'm a little wary about the fact that they did not use 3 significant figures in your text. I don't know why. There should be a third decimal place. All right, compound interest. You have all done this before. Compounding, we also talked about it in the section prior. Looking just to make sure, compounding annually, your n value would be 1. Semi-annually, your n value would be 2. Quarterly would be 4. Monthly would be 12. Daily would be 365 days. Or is it 364? I think it's 364 days in a year, isn't it? I hope so. And then in a leap year, it's 365. Am I confused because it is leap year? Maybe. All right, so other things to remember. This is our initial amount. So the formula that they gave you here was with a P. So I will use P. This here is your R, which would be 0.0525. And then after 8 years, T is equal to 8. And then they ask you to do any of those, which you should be able to easily put into the formula. We can do quarterly, which would be that A is equal to, and I think they use A. Sorry about the back and forth. A is equal to 1,000 times 1 plus 0.0525 divided by quarterly times 4 2 times 8. And remember, I always said simplify that to 32 before you put that in the calculator. New car is purchased, $22,000. If the value of the car depreciates, so we're depreciating, A is equal to P times 1 minus R to the T. So what will be the approximate to the whole dollar in 4.5 years? So A of 4.5 would be equal to the initial amount of the car times 1 minus depreciating 15% to the 4.5. So depreciating 15%, you'll notice, is the same thing as a B value of 0.85. All right. The number E, I did want to put up this table because I wanted to show you the definition of E. You should know the definition. It's the limit as n goes towards infinity. So the table below actually shows the increasing n values. So here n is equal to 1 and your value is 2. But as you keep going, you get to 525,600. You'll notice that the value is getting closer and closer to the value of E. So again, the limit as n goes to infinity is going to be E.